Hi everyone, welcome back to our next lesson with matrices. Today we are going to discuss inverses and solving 2 by 2 matrices. So the inverse of a matrix is when you raise it to the power of -1. That is the button that you've been pushing on the graphing calculator the last couple of days when you've been doing your entering your matrix into the calculator. In order to determine the inverse of a 2 by 2, we are going to take the elements of A and D, so row 1 column 1 and row 2 column 2, and swap places. And then the other two elements, B and C, that's row 1 column 2 and row 2 column 1, we are going to change their signs. Then we will divide each of those elements by the determinant, which is AD minus BC. And a couple of quick reminders, not all matrices are going to have an inverse. So if you see singular matrix as an answer choice that comes up in your graphing calculator, then that means that there is no inverse for this particular matrix. And what actually is an inverse? So it's an operation that undoes another one. So quick examples, addition and subtraction are inverses. Multiplication and division are inverses. X squared and the square root of x squared. So if I square an x and then I take its square root, those two things undo each other. Or likely if I had something raised to the third power and then I took the cubed root of it, those two would undo each other as well. So cubing and taking the cube root. So using an inverse matrix undoes the original to help us solve for a solution as we go through. And it will also give us the identity matrix if we multiply the original by its inverse. And what is an identity matrix? So after we go through a couple uses, we'll discuss that identity matrix. One of the main things we can use matrices for is to solve a system of linear equations. So back in Algebra 1, you did examples like y equals 2x plus 7 and 3x minus 2y equals 8, and you were looking for the point of intersection. So you could use substitution or elimination, or you could even graph the two and then find the intersection point if there was one for these two lines. We're still going to be doing the same thing, but we're going to be using our matrices instead. So real quick, some math humor. How does a farmer count a herd of cows? I'm sure you've heard this one. A calculator. Haha, funny, funny. All right, real quickly, just a practice of matrix multiplication. Matrix A is a 2 by 2 and matrix B is also a 2 by 2. So it doesn't matter the order of these because either way the rows of the second matrix are going to match the number of columns for the first matrix, and you should always get a 2 by 2 when you actually go through and solve them. So just a quick practice, we are going to take AB and multiply them. So I'm going to take row 1 and multiply it by column 1, and that would give me 2 times 2 plus 6 times -1/2. That's supposed to be a 6. So that would be 4 minus 3, which is 1. So that'll be my first element. And then I can do row 1 multiplied by column 2 to get my next element, and that will give us 2 times -3 plus 6 times 1, so that's -6 plus 6, which equals 0. So the elements of the first row of AB, the product, gives us 1, 0. We're next going to multiply. Now we've taken care of everything in row 1, so we don't have to look at that one anymore. Now we're going to take row 2 and multiply it by column 1, and that gives us the values of, let's see, 1 times 2, let's say it in the right way, plus 4 times -1/2. So that would be 2 plus a -2, which is 0. So that's the row 2, column 1 element. And lastly for this one, we're going to take row 2 and multiply it by column 2, and that would give us 1 times negative 3 plus 4 times 1. So negative 3 plus 4 gives us a negative 1, or excuse me, gives us 1, positive 1, excuse me guys. All right, so those are the elements of BA. If we are to multiply the other direction and actually we did AB, and now we're going to multiply the other way and do BA, we should see that we get similar answer to what we started with on this example. All right, so I'm going to do row 1 by column 1 for B times A. So that is 2 times 2 plus negative 3 times 1. So that would be 4 minus 3, which is 1. There's my first element. Okay, then we'll do row 1, column 2, and the product of those is 2 times 6 plus negative 3 times 4. So that will give us 12 minus 12, which is 0. 12 minus 12 is 0. There we are. Okay, so I took care of row 1. Now we're going to move down to row 2, and we're going to look at row 2 multiplied by column 1, and those elements will give us negative 1/2 multiplied by 2 plus 1 times 1. So negative 1/2 of 2 would be 1, negative 1, and negative 1 plus 1 would give me a 0. So that is row 2, column 1's element. And our last example, row 2 by column 2, and that will give us negative 1/2 multiplied by 6, which is negative 3, plus 4 times 1, which is 4, so that gives us a value of 1. Okay, so you notice in this case when we multiplied A times B or B times A, it didn't matter. We got the exact same elements in each of them. All right, so in our last slide, when we multiplied A times B and B times A, those two matrices, we actually determined the identity matrix for a 2 by 2 matrix. And the identity matrix means that if I multiplied it back by either the original matrix or its inverse, either way, I would get what I started with. And it also proves that the two matrices that we multiplied together, matrix A and matrix B, those are inverses of one another because they undid each other and gave us the identity matrix. Okay, so a 3 by 3 identity matrix has 3 rows and 3 columns. The first row will be 1, 0, 0. The second row is 0, 1, 0. And the third row is 0, 0, 1. Okay. Let's see if you hopefully have picked up on the pattern and can maybe do a 4 by 4 identity matrix. Okay, what do you think it should start with? Each of my others in row 1, column 1 have started with 1 and filled in the remaining elements with a 0. In row 2, column 2, each of those elements are a 1 and the other surrounding elements are zeros. Okay, and then when I did my 3 by 3 in row 3, column 3, so row 3, column 3 is a 1 and each of the other elements are zeros. So hopefully you've picked up that in row 4, column 4, that last element is going to be a 1 and each of the other elements are zeros. So hopefully you've looked at each of them and compared and noticed that you have 1s down the diagonals from the row 1, column 1 to the opposite side, from the very first element to the very last element. You have 1s down the diagonals, and everything else is a 0. All other elements are zeros. So again, if you multiply two matrices together and you get the identity matrix, just like we did in AB and BA in the last slide, you'll see that they are inverses of one another. Okay, so in this next slide, we are going to use matrix A with elements A, B, C, D in order to determine its inverse. And we're going to use this formula so that we can do it by hand. So A inverse is 1 over the product of AD minus the product of BC multiplied by the original matrix. But if you notice, the first and last, the A and the D elements have switched places, and the B and the C elements have changed signs. And that AD minus BC, do you guys remember what that is? We talked about it in the last lesson. Hopefully you remember that it is the determinant. Okay, so we're going to do 1 divided by the determinant and then multiply that through to the elements of the matrix after I've switched places for first and last and changed signs of the other two. Okay, so here's our first example, example A, and we need to determine the inverse of A. Again, that's 1 over the determinant, and I'm going to go ahead and switch my places. So A and D switch places, the 1 and the 3, and then the signs change for the other two. So row 1, column 2 is a positive 2, and row 2, column 1 is now a negative 4. Okay, that's my setup. Next, I'm going to take a little note off to the side and figure the determinant, and that is the down diagonals, 3 multiplied by 1, minus the product of the up diagonals, 4 multiplied by negative 2. So 3 minus negative 8 will give me 11. So we now have, we can substitute that as our determinant. So I have 1/11 multiplied by 1, 2, negative 4, 3. Okay, so when you distribute, since that numerator is a 1, you're basically taking each of the elements and just dividing them by the determinant. And if the fraction can simplify, you should simplify it just to make life a little bit easier and look a little bit cleaner. There you go. So the inverse of matrix A has elements of 1/11, 2/11, negative 4/11, and 3/11. Okay, so the inverse of matrix B, or B inverse, is going to be 1 divided by the determinant multiplied through by, switch your places of your first and last elements, change your signs of the remaining elements. Okay, take a side step and do the determinant for matrix B. That is the product of the down diagonals minus the product of the upward diagonals. So we get 6 minus 6, which is 0. We will then substitute that back into our formula. So B inverse is 1 divided by 0, which gets multiplied by the elements 6, negative 2, negative 3, 1. Okay. Can we divide by 0? Question mark. Not sure? If you're not sure, type in your calculator, see what happens. Do 1 divided by 0. It should say that 1 divided by 0 is undefined. Okay, so if you were to distribute through, you would see 6 over 0, negative 2 over 0, negative 3 over 0, and 1 over 0. And that does not work. Okay, if you ever have a determinant equal to 0, then that means there will be no inverse for this particular matrix. It does not work because you can't divide by 0. And in your calculator, it'll give you a note that it is a singular matrix. It doesn't mean you did anything wrong. It just means that there is no inverse for this particular matrix. If you check it and just double check and make sure that you have your elements listed correctly in your graphing calculator, and you do the inverse again using your graphing calculator and still get singular matrix, then you should know you're good to go. It does not work. Okay, so now we're going to go to the applications of using the inverse in order to solve a 2 by 2 matrix equation. So the example that you have below, 2x plus 3y equals 8 and 4x minus y equals 2, that is a system of linear equations. So the methods that you would use to try to solve the system of linear equations would be to graph, or to use the substitution method, or lastly, you could use the elimination method. You had those three choices. And if you're graphing two lines, any two lines, you were looking for the point of intersection. So you're looking for the XY coordinates where those two lines would intersect on the graph. Personally, in this example, we'll just run through it just to kind of brush up on some skills. I think the elimination method is easiest. Because I can make the y values be exact opposites pretty easily, or I could make the x's be exact opposites. So I'm going to go ahead and eliminate the y values. I'm going to keep the first equation exactly as it is. And then the second equation, if I multiply every term by 3, then I'll have a 12x minus 3y equals 6. And in this case, now when I add those two equations together, the y values eliminate and I get 14x to equal 14. So I've determined that my x coordinate is 1. So when I find that point of intersection, I already know that the x coordinate is 1. Now here's where you have a choice. You're going to substitute x, its value, back into either of the two equations that you have. We'll just go with the first one because it's first. So it's 2x, or 2 times 1, plus 3y equals 8. 2 times 1 is 2. Excuse me, that should be a 2. That does not look like a 2. So it'll be 2 plus 3y equals 8. We'll use an inverse operation by subtracting 2 on both sides to get 3y equals 6. And lastly, another inverse operation dividing both sides of the equation by 3 to give us a y value of 2. So our point of intersection, if I were to graph those two linear equations, they would intersect at the point 1, 2. Okay, in our next slide, we're going to learn how to use a matrix equation to solve this exact same system. So, exact same system. We have 2x plus 3y equals 8 and 4x minus y equals 2. The first step says write the equation as a matrix equation. Next, it talks about a coefficient matrix and a solution matrix, and finally get an ordered pair as a solution. Okay, I'm going to change solution matrix. That's kind of my silly word of calling it, but it really is the constant matrix because we're going to use the constants. All right, so a coefficient matrix, that means what are the numbers in front of the variables? Okay, so I have a 2x and a 3y, a 4x and a negative 1y. Those are the coefficient matrix values, excuse me. I'm going to multiply that by a variable matrix. The variables are x and y. And if you quickly checked, 2, 3 multiplied by xy, row 1 by column 1 would give me 2x plus 3y, which is that first linear equation, and row 2 by column 1 would give me a 4x and a negative 1y, which is the second. So I know I've set that up correctly. Okay, and then that will equal our constant matrix, which would be the elements 8 and 2. Okay, so by hand, in order to get the x and the y by themselves, okay, I can't just divide through by a coefficient matrix. I have to take its inverse, okay? So I'm going to get the xy by itself by taking my coefficient matrix, 2, 3, 4, negative 1, determining its inverse. Remember, that is the x to the negative 1 button on your graphing calculator. It will do all the work for you guys. I know we just did it by hand, but it will work if you do this as well. And then after I've gotten the inverse of that first matrix, you can call it matrix A, you then multiply it by the constant matrix, which you could call matrix B. So Whether you do it by hand or whether you do it in the graphing calculator, your solution should be the same thing that we had the last time. And those elements were 1, 2, or the ordered pair 1, 2. All right, so quickly I'm going to show you the work of getting the determinant, getting the inverse, and then multiplying through. So the determinant of the coefficient matrix is going to be -2 and then minus 12. So -2 minus 12, which gives me -14. And I'm going to take the inverse, so let's call it matrix A to make it easy. So A inverse is going to be 1 over -14 multiplied by, change the places, so -1 and 2 for the first and last, and change the signs of the others, -3 and -4. When I distribute through, I will get that the inverse of matrix A, or that coefficient matrix, is +1/14, +3/14, +4/14, and -2/14. You don't need to simplify them right now because we're using it to solve an equation, so we can go ahead and just continue on. So there's the inverse of A, or those coefficients. We will then multiply by 8/2, and we should get those values of +1 and +2. So I'm going to take row 1 and multiply by column 1. So 8 times 1/14 is 8/14, plus 3/14 times 2 would give me 6/14, which is 14 over 14, which equals 1. There's my first element. Now I'm going to do row 2 by column 1. 4/14 times 8 would give me 32/14. Ooh, that's big. And -2/14 times 2/14 would be a -4/14. So 32 minus 4 gives me a numerator of 28 over 14, and 28 divided by 14 is 2. So this is the long way. Again, you can type it into your graphing calculator, hit the inverse button, and let it do the work for you. You should still get an ordered pair of 1, 2 for this example. Okay, our next example, we are going to practice setting up. I need the coefficient matrix, the variable matrix, and that all needs to equal the constant matrix. I'd like for you then to practice your skills using the graphing calculator and set up your matrix equation, how you're going to type it into the graphing calculator. So my coefficients are 2 and -1, 1 and +2. The variables again are just x and y. I have a system of 2 linear equations, and the constants are -7 and -6. So my setup to determine the values of x and y, the point where these two lines might intersect, would be the inverse of the original. Okay, so again, I'm not doing the work. I'm letting the calculator do the work for me in this example, so I'm just going to set up the matrix as it is, 2, -1, 1, 2. I will raise it to the power of -1. Again, that is the x to the -1 button on your calculator. I will then multiply that by the constant matrix. Enter each of these into your calculator, column A and B. Make sure you have the correct dimensions. A is a 2 by 2 and B is a 2 by 1. And when you multiply these, okay, so again, those solutions should be -4 and -1, or as an ordered pair, -4, -1. There we go. All right, our next couple of examples are actually going to be word problems, so we are going to have to read through the word problem, pull out the important information so that we can write two different equations, and then we can set up our matrix equations and solve. And just be really mindful, read your problems through one full time, and then go back and pick out the necessary info so that you don't get junked up with all the extra stuff. All right, so student tickets at a football game are $5. Adult tickets are $7. A total of 1,487 tickets were sold, which resulted in total sales of $9,113. Determine how many of each type of ticket are sold. Okay, so the information that we're given, they talk about student tickets and adult tickets. So I'm going to let my X values equal student tickets, and I'm going to let the Y variables equal the adult tickets. It doesn't matter which way you choose them or what variables you choose, as long as you're consistent through the entire problem. All right, so now we're going to try to write our two equations. The first one tells me that the student tickets are $5. Okay, so I'm going to write a money equation. I've got $5 per student ticket plus $7, it's at $7 for an adult ticket, and that will equal the total amount of sales, $9,113. Okay. My next equation I'm going to use is to determine the total number of tickets sold. Okay, so the number of tickets. How many student tickets were sold? We don't know. And how many adult tickets? We don't know again, but that has a sum of 1,487 tickets. Okay, so those are our two linear equations. We can then set up the matrix equations based upon the coefficients, variables, and constants. So our coefficients are 5, 7, 1, 1. The variables are the x and the y. Again, you can choose other variables, and that will equal the constants, which are 9,113 and 1,487. Okay, so to solve for x and y, the number of student tickets and the number of adult tickets, we need to take our coefficient matrix 5, 7, 1, 1, determine its inverse, and then multiply that by the constant matrix. Okay. So when you've typed all of this into your calculator, again, double, triple check your work. We should determine that our x value is 648 and our y value is 839. Okay, so in this case, I don't need to really write that as an ordered pair as the point of where they intersect, but you could quickly write a little note. 648 student tickets were sold. Let's see, student tickets sold, and 839 adult tickets sold. Sorry, my handwriting got so yucky. There you go. If you can write that sentence at the end, and not only proves that you got the correct answer, but that you understand it in terms of this particular example. So that's like top notch right there. All right, our last example, Mora. This is actually my sister-in-law. Love to use my family names in my word problems. So she's planting romaine lettuce and Roma tomatoes in her raised bed garden. It has 24 square feet and should yield 18 plants. All right, so right now, I know I've got lettuce and tomatoes, so I kind of got that on the brain to give my variables. The lettuce takes up 2 square feet per plant and the tomatoes take up 1 square foot per plant. How many of each should she expect to yield? All right, so I'm going to stick with X's and Y's. Lettuce came first, so lettuce is going to be my X's, and tomatoes came second, so they will be my Y's. All right, so the next sentence says the raised bed, which is 24 square feet. All right, so I'm going to talk about the area of the square footage of the raised bed. Okay, there's a total of 24 square feet. Now I need to look to see how much each of those plants is going to take up. So the lettuce takes up 2 square feet, so that could be 2x, and the tomatoes only take up 1 square foot, so plus 1y. That'll equal a total of 24 square feet. Okay, not too bad. The next part in that same sentence, the raised bed, which is 24 square feet, should yield 18 plants. So now we're going to look at the total number of plants that she should get. And that's actually what we're trying to find. So we don't know how many lettuce and we don't know how many tomatoes, but we know it should yield a total of 18 plants. Okay, so there are our two linear equations. We are now going to write the coefficient matrix of 2, 1, 1, 1. We're going to multiply that by the variable matrix xy. We're going to set that equal to the constant matrix 24, 18. Again, showing our work before we put it into the calculator, we are going to take the inverse of the coefficient matrix and we will multiply it by the constant matrix. And your solution should be 6 and 12. Okay, so again, what does that mean in this particular example? So it means that we have a total of 6 lettuce plants and 12 tomato plants. Now that doesn't tell us how well the lettuce plants are going to do and how many tomatoes are on each tomato plant, but how many of them should grow in that square footage. All right, these are the calculator instructions to help you remember. They're also online, so you could print them out as needed. And you can work through worksheet F, the 2x2 matrices and solving equations practice. And lastly, you do have another quick little quiz at the end of this week. That shouldn't take us any time because we're just doing 2x2 and 3x3 matrix equations.